Welcome to using the derivative operator. So quick definition, the derivative operator which is typically denoted with a capital D, is defined by dy is equal to the derivative of y. It turns out we can actually rewrite ODEs with the derivative operator. In order to do this, we need to use a quick fact. So just note that if we want to take d to the k y, this just means that we are applying d k times in a row on y. But that just means that we are applying the derivative k times in a row. So we're applying the derivative k times. And that is just precisely the kth derivative of y. So essentially, we can just replace all of our kth derivatives of y with d to the ky when we update the screen. So again, essentially what we can do is we can replace each of the derivatives, kth derivatives, with d to the ky. So for example, let's go ahead and rewrite the differential equation, the third derivative of y minus 2 times the second derivative of y plus 5y prime minus 10y equals 0 using the derivative operator. So again, y is just y, right? Y prime is dy. The second derivative is d squared y, and that third derivative is d cubed y. So we wind up getting d cubed y minus 2d squared y plus 5d y prime minus 10y is equal to 0. And then we can rewrite this in an alternative format. So we can rewrite this as the operator d cubed minus 2d squared plus 5d minus 10 on y is equal to 0. So we call this d cubed minus 2d squared plus 5d minus 10 a polynomial operator. No, just like we can factor polynomials, we can factor polynomial operators. And so if we have, if P of D can be written as Q of D times R of D, which is equivalently R of D times Q of D. Essentially, these are actually our equivalent. Meaning that for all y, they give the same answer. So P of D y is equal to Q of D applied to R of D y is equal to R of D applied to Q of D y for all y. So what we get is that if P of D equals 0 is the 0 operator. Sorry, P of dy equals 0. In other words, y is a solution to the homogeneous equation. Then sorry, I have this backwards. So if R of D y is equal to 0, then so is P of D y, right? And similarly, if Q of D y is equal to 0, then so is P of D y. You can see this just simply by using those two alternative forms, right? So if R of D y is equal to 0, then we would just have Q of D evaluated as 0. And of course, any derivative of 0 is 0. So this would go to 0, right? Similarly for the R of D applied to Q of D y. So this gives us a nice convenient tool to use. So we can essentially reduce our equation to a lower order equation, or reduce our problem to a lower order problem. So for an example, let's use the derivative operator to find the general solution to the third derivative of y minus 2 times the second derivative plus 5 times the first derivative minus 10y equals 0. Note this is the same equation we were working with earlier. So we have d cubed minus 2d squared plus 5d minus 10 all applied to y is equal to 0. We can go ahead and factor that d cubed minus 2d squared plus 5d minus 10. This winds up factoring as d minus 2 times d squared plus 5 y is equal to 0. So what we get is that if d minus 2 y equals 0, then y is a solution. And similarly, if d squared plus 5 y equals 0, then y is a solution to our original equation. So does d minus 2y equaling 0? This just means that dy minus 2y is equal to 0. And of course, dy is just y prime minus 2y equals 0. And so we get a solution of the form y1 is e to the 2x. Similarly, if we look at d squared plus 5y equals 0, this is d squared y plus 5y equals 0, or just the second derivative of y plus 5y is equal to 0. We have already seen how to solve these problems before. This winds up giving us y2 is equal to cosine of the square root 5 times x, and y3 equal to sine of the square root 5 times x. And we wind up getting then that our general solution is y is equal to c1 e to the 2x plus c2 cosine of the square root 5 times x plus c3 times sine of the square root of 5 times x. So essentially, we've boiled our problem down from a third order equation to a first order equation and a second order equation. We could check the Wronskian to prove that this is our general solution. I am not going to do so at the moment. In the next video, we will look at sort of the various types of solutions we can wind up with nth order homogeneous linear constant coefficient ODEs.